Hello, statistics students. Here's another video on the analysis of variance, example 2. We saw in the last example that we were calculating the F statistic by looking at the variation between the groups and dividing that by the variation within the groups. But we didn't talk about how to measure the variation between the groups. We just looked at it visually and said that in the first case, the variation between the groups, the means were pretty close together, so that variation was small. In the second case, it was big. Now, as in past hypothesis tests, we can use statistical software packages to help us determine the result of the test. So most statistical software packages produce something called an ANOVA table. This table includes lots of information, some of it redundant, including the value of the F statistic. This next example that we show has an example of one of these ANOVA tables. So I know that's kind of small, so let's increase the font size on that a little bit to visualize or view that a little bit better. Okay, so we're talking about marital status and cholesterol. Refer to the StatCrunch output from National Health and Nutrition Examination Survey data, which shows the association between marital status and cholesterol. Assume the population distributions are close enough to normal to justify using ANOVA. Part A says write the null and alternative hypotheses for the association between marital status and cholesterol. So we've got how many groups here? We've got marital status of divorced, living with partner, married, never married, separated, widowed. So that's 6 groups. And each of those 6 groups will then have a mean cholesterol level. So we see the divorced have a mean cholesterol level of about 212.5, living with partner about 198.3, and so on. Letter A, write the null and alternative hypotheses. Remember, the null hypothesis always says that there is no association between the groups and the cholesterol level. And so the generic statement is the population means are all equal. In terms of our statement, is we say that marital status and the mean cholesterol level are not associated. The alternative is the opposite of this. The opposite of the population means are all equal is at least one of the population means is different from another. In terms of our scenario, is marital status and cholesterol level are associated. Part B, identify the F statistic from the StatCrunch output. So we search around in there until we finally find the F statistic here. And so that F statistic is 9.14200934. C, which marital status had the largest sample mean and which had the smallest sample mean? So we look here, and divorced was 212, living with partner was 198, married was 208, never married was 184, separated 208, and widowed 209. So it looks like the never married was about 184.49457. And the largest one, 212.52564, the divorced. And the smallest sample mean was never married at 184.49457. So in a later video, we'll talk about how to look at the F statistic to determine if we have enough evidence to reject the null and to say that at least one of the population means is different from another, or the marital status and cholesterol level are associated, meaning we found an association between marital status and cholesterol levels. But for right now, we just say, assuming that we did find this, does this association mean causality? Does it cause different cholesterol levels? So remember, we said in a controlled experiment, in a random controlled experiment, if we have association, then we can deduce or conclude causality. But in this particular example, it nowhere talks about that this was an experiment. So we can only conclude that it's not a random controlled experiment, that this is an actual observational study. Since this is an observational study, we cannot conclude causality. The marital status did not, or we cannot conclude that the marital status causes different cholesterol levels. It may be true, but we just can't conclude that from this observational study. Now, can you think of a confounding factor? It's the random controlled experiment that takes out the confounding factor. So a confounding factor is a variable that's hidden in here somewhere that could have an effect on both of our variables, the marital status and the cholesterol level. In this particular example, we just have people that have some different kind of marital status. Some people that are never married could be really young and will have low cholesterol. We could even have some people that are old that have never been married that'll have typically higher cholesterol. So age is a confounding variable because young people are typically not married. And young people typically have lower cholesterol. And so it's this confounding factor or confounding variable that hinders our conclusion of causality. And this concludes the video on the example 2 for the analysis of variance.